No. Whoops, great. And then somebody gives me a phone call. T. Mark Harrison calling at a very bad time. Anyhow, okay, well, I'd like to just say a few words of welcome to our speaker today, Alan Rubin. Even though I'm sure most of you know Alan, you may not know everything about Alan. Probably very few people know everything about Alan. Sorry. All right. All right. Hopefully he'll get the message. Sorry about that. And so let me just say, Alan, some of you may not know, his undergraduate degree is actually in astronomy. And then somewhere along the line, he decided that he would rather hold the things that he was studying rather than just look at them from afar. And so he switched to geology and went to the Institute of Meteoritics at University of New Mexico for his PhD. He's had a long career at UCLA, recently retired from that career, but still active, as you can see. Alan's written, I don't know, more than 200 research papers about meteorites. And he's about to publish, or you're just publishing your 4th book.
Later this year, it comes out.
Later this year. However, only 2 of the books are about meteorites. So,
well, there's a fair amount of meteorites in the 4th one as well.
Okay, that's the one on geometry, which
right.
But that's not out yet. But the meteorite books, I guess, will be for sale in the lobby after the lecture. The author can sign them. So there you go.
Well, the geometry book is available for pre-order on Amazon.
Well, there you go. You should bring a, you know, how the people promote up. There you go. This is a promotion.
It's called /volume.
All right, we can sort of see it a little bit there. It's fading into the iron meteorite behind you.
All right.
So today he's going to talk to us about the 2E irons, the most reduced group of ordinary chondrites. But before I let him start, I wanted to just say that there's one additional rule for today's seminar, which for the chat room and for the discussion. You've heard about wearing two hats. Well, today I have 2 shirts. So I've got my Meteor Crater shirt, but then right after this, the New York Giants shirt will go on. And so there's to be no discussion of the score on the Giants-Vikings game, which is going on right now and is being recorded. So thank you very much for abiding by that. I would greatly appreciate it. And now we'll turn the floor over to Alan.
Okay, thank you, Kevin. And thank you all for navigating your way here in the unusual circumstances. I'll be talking about 2E irons and talk about them as ordinary chondrites, which might seem a little perverse, but we'll get into it. So I'll start off with a new hope. A long time ago in our galaxy, far, far away from any point outside the local group, the 2E irons formed as the most reduced ordinary chondrites. The 2E irons were first created, the group was first created by Ed Scott and John Wasson in 1976 in this paper in GCA, along with a couple of other groups. And it was an unusual group from the start. If we look at this diagram of here, cobalt versus gold, we'll see that for most iron meteorite groups, like the 2C, the 2F, the 2D, the 4B, and so forth, they most have these lines here are composed of individual samples. These bulk compositions plot an element-element concentration diagrams like these inside narrow arrays, which we can see, which have slopes which are consistent with having formed by fractional crystallization within well-mixed metal magmas in the cores of asteroids. These are called magmatic irons. Again, they're derived from the cores of differentiated asteroids. But if you look at a couple of these groups, the 2E, here shown by these red arrows, and the 1AB, these are non-magmatic irons. They have slopes inconsistent with having formed by fractional crystallization on these element-element diagrams. They're modeled as having formed in the near surface regions of chondritic asteroids, presumably by impact processes. Well, if you look at an undifferentiated, unmelted asteroid, a chondritic asteroid, if you will, the metal and the silicate are homogeneously distributed, sort of like this, where the metal and the silicate are the concentrations of the metal near the surface are sort of similar to the concentrations of metal in the center of the body. So these primitive or undifferentiated meteorites, these chondrites, have metal grains and silicate grains mixed together. Here's a equilibrated chondrite, faucet, where we see the metal grains is sort of these white grains that are more or less homogeneously distributed. The silicate is sort of the darker gray material here. If we look at, so let's just put that aside. And so if the 2E irons are rather different than that. Here's one of the 2Es, columera. The sizes of the vast majority of these parental taenite crystals, the big crystals of metallic iron that crystallized from the metal melt, are only 2 to 4 centimeters in size. They're far smaller than the parental taenite crystals in magmatic irons, those formed in asteroidal cores, which can be up to 2 meters in size in, for example, the Cape York 3AB iron. The 2E irons are structurally varied. There are coarse octahedrites, medium octahedrites, fine octahedrites, finest octahedrites, as well as some unusual polycrystalline kamacite aggregates. So although most magmatic iron meteorite groups have meteorites that by and large have very similar textures, the 2Es violate that standard. There are 2 compositional sets of 2E irons. There's the main set, which is relatively low in copper, and then there's the copper-rich set, which is higher in copper. The main set here is in yellow, and I have the copper outlined in this red rectangle. We can see that the main set contains on average about 222 micrograms per gram of copper. The copper-rich set contains about 363, appreciably more. These copper-rich samples are also rich in trollite. In fact, even though some of the main set samples contain no trollite at all, the copper-rich samples can contain up to about 1/3 of the volume in trollite. If we plot the copper versus gold diagram over here, we can see a very nice dichotomy here between the main set and the copper-rich set. So I want to just talk about how the 2E irons are chondritic. The initial strontium-87-86 ratios in the 2E iron columera and Kodak canal are consistent with derivation from a source with a chondritic rubidium-strontium ratio. The 2E silicates have moderately high abundances of primordial argon-36 and xenon-132, again, consistent with derivation from a chondritic source. 2E metal is essentially identical to the metal in ordinary chondrites in molybdenum and ruthenium isotopic compositions. Here's a 2E iron Watson. It contains this large chondrule-free silicate inclusion with an H-chondrite-like bulk chemical composition. The silicate fractions of 4 2E irons, Netschaëvo, Tecado, Gary-Yassen, and Mount 2, consist of highly recrystallized type 6 metal-rich chondrule-bearing clasts. They have chondrites in them. Here are the chondritic clasts in the meteorite Netschaëvo. Minerals in the Netschaëvo class include olivine, orthopyroxene, calcium pyroxene, sodic plagioclase, marylite, chlorapatite, the phosphates, chromite, trollite, charbicite, kamacite, and taenite. And what's interesting about that is that these are the same phases that occur in equilibrated ordinary chondrites. The clasts in Netschaëvo contain relatively familiar ferromagnesian chondrules. They contain barred olivine, porphyritic pyroxene, porphyritic olivine pyroxene, radiopyroxene, and barred olivine, porphyritic olivine pyroxene chondrules. They range in diameter, apparent diameter, from 240 to 1200 microns. Here's a few examples of these chondrites from an old paper by Ed Olson. Tarahumara is shown over here. Many of the 2E irons, in addition to, or let me put it again, instead of containing these chondritic clasts with chondrules in them, many of the 2E irons contain alkali-rich clasts with non-chondritic bulk compositions. Major phases in these clasts include green chromium diopside, as we see in this picture here, also sodic plagioclase, potassium feldspar, silicate-rich glass or tridymite, and orthopyroxene. There's generally little or no olivine. So this was a puzzle for a long time on why these 2E irons contain these alkali-rich clasts, and many crazy models were promulgated to explain the origin of these clasts. Then back in '86, I showed that these alkali-rich clasts and 2E irons were very similar to these melt pocket glasses in ordinary chondrites that have been analyzed by Gene Jarosevich and Bob Dodd. We can see over here on the right of the screen, the melt pocket glasses are very rich in sodium and potassium compared to H chondrite falls over at the extreme right. And the composition of these silicate inclusions and 2Es are very similar to these melt pocket glasses. These formed in situ by impact melting in ordinary chondrites. Because plagioclase has a low impedance to shock compression, plagioclase melts preferentially as a lower melting point. And so when you have these impact energy coming in, you preferentially melt the plagioclase in situ and you get these alkali-rich melt pocket glasses. These are alkali-rich because plagioclase is rich in these in alkalis, in sodium and potassium. So the conclusion is that 2E irons formed from chondritic material probably related to ordinary chondrites, but we can go a lot farther than that. Okay, let's look at ordinary chondrites for now. Here's a Vinales fall from Cuba from 2019. You can see that it's fairly shocked. It's a nice rock. There, as many of you know, a bit of a review here. There are three major groups of ordinary chondrites: H, L, and LL, standing for high total iron, low total iron, and low total iron, low metallic iron for LL. These groups vary systematically in many mineralogical, chemical, isotopic, and physical properties, and most of these variations result from differences in oxidation state. Probably you haven't gone over many of these changes, but I'll go over all of them now in excruciating detail. And going from H to L to LL, there are these differences. There's decreases in the mean bulk metallic iron, nickel, cobalt abundance as the iron 0, metallic iron, changes to ferrous iron, iron 2+. So now you have more ferrous iron. So therefore, there are increases in the FeO contents of olivine, low-calcium pyroxene, chromite, and ilmenite. There are also increases in the cobalt and nickel concentrations in kamacite because there's less metallic iron there, and so the cobalt and nickel concentrations go up. There's increases in the germanium content of the metal fraction because germanium is more noble than iron, and as iron leaves, the germanium concentration increases as well. There's decreases in the kamacite to taenite modal abundance ratio because less metallic iron is available to form kamacite, and so preferentially the kamacite goes down and the taenite, the low iron nickel rich phase, increases in relative concentration. There's higher olivine to low calcium pyroxene ratios because more iron 2+ becomes available to enter olivine, which has a divalent cation to silicon ratio, twice that of low calcium pyroxene. There's also decreases in the total iron content and going from H to L to LL. Because there's decreases in the total iron content, there's decreases in bulk density. And there's also now to the geochemical parameters, there's decreases in the bulk lithophile to siderophile element ratios, the metal silicate fractionation, for example, the nickel to magnesium ratio. There's also lower refractory siderophile to common siderophile ratios like iridium nickel, that's decreasing. There's also decreasing refractory siderophile to volatile siderophile ratios like iridium gold. And also going from H to L to LL, there are heavier oxygen isotopes, heavier germanium isotopes, and increases in mean chondrule size. We have all of these 14 parameters which change systematically from H to L to LL. So if 2E is going to be an ordinary chondrite group, I would have to show that 2E lies along an extension of these trends. In fact, that's what I'm going to do. We can go from LL to L to H to 2E. I detailed a lot of this in a paper last February in 2022. Okay, here are a bunch of parameters. I picked up some Netschaëvo clasts that I analyzed in 1990, along with equilibrated HL and LL chondrites. Let's look at the olivine phthalate content over on the left. Going from LL to L to H, we go from 29 to 24 to 18 to 14, also to Netschaëvo, again, along an extension of decreasing olivine phthalate. Let's look at the orthopyroxene ferrosilicate contents going from 24 to 21 to 17 to 14. Again, Netschaëvo, the 2E class lie along an extension of the LLLH trend. The kamacite cobalt content goes from 77 milligrams per gram in LLs to 8 to 4.7 to 4.5 in Netschaëvo. Let's skip kamacite nickel for just a second. Let's look at the modal metallic iron nickel abundance. We see that varies from 14 in Netschaëvo, very high, 7.5 in H, 3.2 in L, 1.9 in LL. And let's look at the chondrule diameter. We go from 550 to 500 to 450, going from LL to L to H, and then 240 in Netschaëvo. Now, there's a little bit of a problem right here in that because Netschaëvo is type 6, it's hard to get a good chondrule size. So we look at the, because during metamorphism, chondrule sizes, chondrules recrystallize and integrate with the matrix. And so chondrule sizes are very difficult to estimate. So we try to get the smallest observable chondrules, and that is Netschaëvo. For example, here in Samarcona, we have very easily discernible, well-rounded, nicely observable chondrules. And in this another LS6, the chondrules are very hard to see. So if we look at the smallest intact chondrule, that will be sort of close to the right diameter for the average chondrule size. Now, I said we're going to skip kamacite nickel here for a moment, but we'll go back to it. Going from LL to L to H, we see that the nickel content goes up from 49.8 to 65.4 to 69.2, but the Netschaëvo is sort of intermediate between H and L's. Why doesn't that follow the same trend? Well, here's why. Because these mean nickel contents are just so variable. The standard deviation is very high. Although the average nickel content decreases clearly from LL to L to H, there's a large range in each group. And so if we had many, many 2Es, I suspect that that would also follow the same trend, but we don't have enough that it sort of falls in this variation over here. Okay, now let's look at some diagrams where it's easy to see how the 2Es fall along these trends. An olivine phaolite versus orthopyroxene ferrosilicate, we can see the 2Es lie along an extension of the ordinary chondrite trend, very clear. Okay, let's look at some of these siderophile element concentration ratios. Okay, let's just look at iridium nickel. Going down from 2E to H to L to LL, we can see that the iridium nickel content consistently goes down in a systematic way. Let's look at iridium gold. Again, it goes down from 4.3 to 3.6 to 3.3 to 2.9. Again, very consistent. The gold nickel ratio, again, very consistent. The cobalt nickel ratio, again, very consistent. The 2Es fall along the trend in each of these cases. Okay, here's iridium nickel versus gold nickel, for example, and we can see that the 2E lies along an extension of the LLH trend. Okay, let's look at oxygen isotopes. Now, the oxygen isotopes of 2Es are not much different than that of H chondrites, but they are a little bit lower in big delta 17O. We can see the systematic trend from LL to L to H here, and 2Es are a little bit lower, but not much. Let's look at a couple of these diagrams. On the left, we have little delta 17 versus little delta 18, and we see that the 2Es over here are just sort of under, but intersecting the sort of H chondrite circle over there. On the right diagram, we have big delta 17O versus little delta 18O, and I showed this red arrow pointing to 2E showed this. One of the 2E circles is beneath that of the H chondrite range. Again, similar to H chondrites, but apparently a little bit lower in big delta 17O. We can sort of see that same trend over here. We can see big delta 17O versus cobalt to nickel, for example. Obviously, cobalt nickel falls along the trend, and the big delta 17O would just slightly lower over here. Okay, let's look at the germanium isotopic compositions of these bulk 2Es. Now, this is a little peculiar parameter. It's defined here at the bottom as of the germanium 74 to 70 ratio of the sample over the standard and sort of this formula. And we see that the 2Es have larger negative values than that of H's, which are larger negative than that of L's, which are larger negatives than those of LL. So again, falls along the same trend. And here's that same parameter of the germanium isotopes versus modal metallic iron nickel, for example. Again, we see the similar trends over here. So the conclusion would be that 2E irons constitute the fourth major ordinary chondrite group. We have a couple of 2Es here and an H6 named Spade thrown over on the left for sport. So let's look at the formation of 2E irons and ordinary chondrites. The ordinary chondrites accreted about 2.14 million years after CAI, is based on chromium 54 by the paper shown over here. The oldest cluster of the 2E hafnium tungsten modal age is about 4 to 5 million years after CAIs. But if aluminum 26 was the primary heat source, the 2E parent asteroid must have accreted about 1.5 million years after CAIs, according to Kroger and Klein in 2019, and Hunt et al. Suggested it had a diameter of more than 120 kilometers. Takunihiro et al. Back in 2004 calculated the mean initial aluminum 26-27 ratio in LL chondrules to be this number here, 7.4 to 10 to minus 6, but it's too low to have caused widespread melting and asteroid differentiation. But because the 2E asteroid appears to have accreted earlier than other ordinary chondrites, it may have been heated sufficiently by the decay of aluminum-26 to have experienced partial differentiation. In fact, Morel et al. In 2020 found that the 2E iron Calamera and Tecado acquired natural remnant magnetization after cooling through the tetratanite formation temperature of 320 degrees. They said that this parent body had an internal dynamo, likely powered by thermal convection caused by core crystallization. This is consistent with the slow cooling rates of many of the 2E irons. For example, Calamera about 6 degrees per million years, Miles about 10, and Netschaëvo about 1.4 to 3. The 2E asteroid likely reached a peak temperature about 1250 K, due largely to the decay of aluminum-26, perhaps augmented by collisional heating. This is higher than the iron-nickel FES eutectic temperature of about 1213 K, but it's still far below the silicate solidus temperature of about 1380 K. A metallic melt would have formed at these temperatures with about 85 weight% FES, and some of this melt may have drained to the center of the asteroid to form a small FeO-rich metallic core, and convection in this core produced the magnetic field. Some of the chondritic material in the crust of the mantle of the asteroid didn't melt, because obviously we have the chondritic clasts remaining. It instead experienced severe thermal metamorphism to petrologic type 6. Some portions retain significant amounts of trolite. I think we have 3, 3.5, 4% in some of these clasts. These slowly cooled 2E irons may be crust or mantle restites formed after the separation of the FeS-rich melt. Now, let's look at the alkali-rich clasts again. They formed from residual chondritic material by preferential impact melting of the plagioclase component. Here's a alkali-rich silicate inclusion in 2E Miles. To remind you, we see that the 2E, the silicate-rich clasts, the alkali-rich clasts, and the melt pocket glasses in ordinary chondrites are appreciably richer in sodium and potassium than H chondrite falls, shown over at the right. This scenario that I've been speculating about is consistent with the inferred rapid cooling of the copper-rich 2E iron, such as HOW88403. This meteorite contains these cellular metal grains, partly surrounded by pincer-shaped trolite grains, which is a petrographic indicator of rapid cooling. For those of you who may look this up, this meteorite is listed in the Meteorological Bulletin as ungrouped, but both Ed Scott and John Wasson, after analyzing it, place it among the 2Es. So let's go back to something else dear to my heart, chondrules. So let's talk about 2E irons and the story of chondrules. It appears that early nebular materials were rich in oxygen-16. CAIs are the oldest materials formed in the solar system, about 4.567 billion years ago. Most CAIs seem to have formed in part from an O16-rich reservoir of composition roughly minus 50 per mil to minus 60 per mil in delta 17 and 18O, relative to SMO, standard mean ocean water. The aluminum-rich chondrules are the most refractory chondrules, are more O16-rich than the normal ferromagnesian chondrules. They may have formed by melting mixtures of ferromagnesian chondrules and small CAI fragments. Aluminum-26 chronometry indicates that normal ferromagnesian chondrules and ordinary chondrites formed about 2 to 2.7 million years after CAIs. They formed from precursors that were poorer in 16O than CAIs. That seems pretty clear. Low FeO chondrules, the so-called type 1 chondrules, they tend to be more O16 rich than the high FeO chondrules, the so-called type 2 chondrules. We can see a diagram over here from Scott and Taylor 83, which shows sort of a typical, stereotypical shape of type 1 and type 2 chondrules. The type 1 chondrules tend to be smaller on average than the type 2 chondrules. The type 1 chondrules are also low FeO, the type 2 chondrules are high FeO. Also richer in phosphorus. So if we look at some oxygen over here, we have the CAI diagram in the upper left. We see that the aluminum-rich chondrules are have somewhat are not as rich in O16 as the CAIs. And then on the right, we have the various chondrules here, and we can see that if we just look at the scale on the diagram, we can see that they're much poorer in O16 than the aluminum-rich chondrules or the CAIs. The aluminum 26 chronometry again indicates that most type 1 chondrules, the low FeO ones, are somewhat older than most type 2 chondrules. This is consistent with well-established models wherein nebular materials became more oxidized with time as metallic iron continued to react with gaseous water molecules to produce FeO. So the type 1 chondrules formed earlier, then as nebulae got more oxidized, more of the metal turned into FeO, and so you got higher and higher proportions of type 2 chondrules. Consequently, this means that the average type 1 to type 2 chondrule ratio, or the low FeO to high FeO chondrule modal ratio, decreases in the unequilibrated ordinary chondrites from H to L to LL. We have the numbers here, 1.25 in H for the ratio, 0.56 in L, and 0.36 in LL. A higher proportion of the low FeO type 1 chondrules in H chondrites implies a lower oxidation state, less FeO. This is consistent with the oxidation state increasing from H to L to LL, and we use phthalate compositions here as a proxy. You can see it goes from phthalate 18.8 in H to 24.7 in L to 29.4 is a mean in LL. These observations suggest that among ordinary chondrites, H chondrites agglomerated earliest, followed by L, and then followed by LL, because the type 1 chondrule ratio, abundance ratio decreases from H to L to LL, and type 1 chondrules seem to be older. I suggest that the chondritic precursors of 2E irons accreted earlier than H chondrites at an epoch when fewer type 2 chondrules were around. The 2E precursors then would have acquired even higher type 1 to type 2 chondrule modal ratios than H3 chondrites. For the 2E chondritic class, this would account for their small average chondrule sizes, smaller than H, and their more reduced state, more reduced than H. The oxidation state of ordinary chondrite whole rocks reflects that of their constituent chondrules because unequilibrated ordinary chondrites are composed primarily of chondrules, 60 to 80 volume percent. The earlier accreted chondrules are more likely than the later accreted the earlier accreted chondrites are more likely than the later accreted chondrites to have incorporated CAIs and CAI-fragments. More of them would have been around in the nebula. This is consistent with the relatively abundant CAIs, about 0.2 volume percent, found at least some of the primitive H3 chondrites, which is about 20 times the value found in typical type 3 ordinary chondrites, which is about 0.01 volume percent. Okay, let's put that aside for a moment and look at the bulk chemical fractionations exhibited by chondritic meteorites. There's the famous metal silicate fractionation that has been bedeviling people since the 50s. These are the fractionation of siderophiles from lithophiles, for example, epitomized by the nickel to magnesium ratio going from 1.04 in H to 0.75 in L to 0.61 in LL. There's also the refractory siderophile to common siderophile ratio, like iridium nickel, going, you see, from H to L to LL. We can see the decrease there. There's the refractory siderophile to volatile siderophile ratio, again shown here, like for iridium gallium, for example, getting lower from H to L to LL. And then there's the volatile siderophile from common siderophile ratio, like gold to nickel ratio. We can see that it decreases from H to L to LL from 0.99 to 0.95 to 0.90. 2E irons lie along extensions of these OC siderophile compositional trends. Here's iridium nickel. We can see over on the left, going from LL to L to H to 2E. We can see these systematic increases. Iridium gold, we can see systematic increases from LL to L to H to 2E. And in gold nickel, a similar systematic increase from LL to L to H to 2E. These trends are caused, at least partly, I contend, by chondrule formation. Grossman and Wasson in 85 concluded that, quote, the common metal component in chondrules is similar to and may be the same as the common component involved in the metal silicate fractionation of the ordinary chondrite groups. The hafnium tungsten data of Hellman et al. In 2019 show that the metal silicate fractionation occurred at about the same time as chondrule formation, about 2 to 2.7 million years after the formation of CAIs. Okay, many CAIs contain these tiny refractory metal nuggets that are rich in refractory siderophile elements like rhenium, osmium, ruthenium, iridium, molybdenum, tungsten, platinum, as well as iron and nickel. We have a few pictures of these RMNs, the refractory metal nuggets, shown here. So many CAIs contain these tiny metal nuggets. So it seems clear that most CAIs formed before most chondrules. The oldest chondrules, the chondrules that formed earliest, most likely acquired the highest proportions of these small CAI fragments, many of which contain refractory metal nuggets. Hence, the earlier formed chondrules would have acquired more refractory metal nuggets and be richer in these siderophile, refractory siderophile component. Also, the chondrules incorporating CAI fragments is consistent with the existence of these compounds, chondrule CAI objects, as shown over here. Factor analysis of chondrule bulk compositions that we did at UCLA many times, years and years ago, back in the 80s, shows that chondrules contain a refractory compositional component. For example, we can see here the aluminum, samarium, scandium is plotting separately. This is likely attributed to melted CAI fragments in the chondrules. They're no longer petrographically observable, but their chemical signature remains. Because most type 1, low FeO chondrules, formed before most type 2, high FeO chondrules, the type 1 chondrules, the low FeO ones, were more likely to have acquired CAI fragments containing refractory metal nuggets. 2E irons are the oldest ordinary chondrites. They have the highest proportion of type 1 chondrules, and they have the highest bulk iridium nickel and highest bulk iridium gold ratios. The formation of the chondritic precursors of 2E irons was followed by the formation of H chondrites, then L, then LL. So here's the metal silicate fractionation. The loss of metal from chondrules during chondrule melting and the subsequent failure of chondrite hole rocks to reacquire this metal quantitatively can account, at least in part, for the bulk metal silicate fractionation. Here's a metal nodule escaping from this cratered radiopyroxene chondrule over here. Metallic iron nickel melts are immiscible in silicate melts, and so during chondrule melting, a spitting molten or partly molten chondrule droplet would tend to expel round metal sulfide blebs along the plane of the chondrule's equator. And here we have a cryptocrystalline chondrule, I guess, that has these two indentations in it, sometimes called chondrule craters. Many of these hemispherical indentations are lined with metallic iron and or sulfide, suggesting these are remnants of expelled opaque globules. Jeff Grossman has suggested that indentations occur in about 10% of ordinary chondrite chondrules. He also found the median diameter of a sphere with the same arc as the typical indentation is 75 microns, as we can see in this picture over here. There are also opaque globules outside of silicate chondrules in ordinary chondrites that were likely expelled from molten chondrules. Here's a picture here of this one has trollite cohenite, an iron carbide, and magnetite. This has been aqueously altered, but it's originally primarily metal and trollite. These opaque chondrules have sometimes been called metallic chondrules. Some type 2 or FeO-rich chondrules have highly fractionated siderophile element compositions. Let's look over at the diagram on the right where we have high FeO. We can see that they're very, very rich in iron and much depleted in gold, arsenic, gallium, selenium, and zinc. This suggests that a lot of the iron was FeO and was retained with the silicates in the chondrule, and the metal components, the metal, the siderophile elements that were not oxidized, were expelled leading to this fractionated bulk composition over here. Because type 1 chondrules constitute roughly 40 volume percent of H3 chondrites, loss of metallic iron nickel rich globules from low FeO chondrules, type 1 chondrules, would cause a significant decrease in the bulk chondrite iron silicon ratio and nickel silicon ratios, accounting for the metal silicate fractionation. This is consistent with the CI normalized nickel silicon ratios of HL and LL being appreciably less than unity. As we can see, the numbers are over here. 0.94 in H, 0.64 in L, and 0.53 in LL. If the metal globules expelled from the chondrules had been quantitatively reacquired by the whole rock, this would not have contributed to the metal silicate fractionation, but the aerodynamic behavior of a particle in the gaseous nebula is a product of the particle's size and density. A 500 micron diameter silicate-rich chondrule with a density of 3.3 grams per cubic centimeter has a diameter density product 3 times higher than that of a 75 micron diameter opaque globule composed of 80% metal and 20% trollite. Most expelled opaque globules would have drifted far away by these aerodynamic processes from the chondrules and would not have been reacquired by the chondrite hole rock, accounting for the metal silicate fractionation. Thus, the loss of metal from chondrules during chondrule melting and the subsequent failure of these chondrite hole rocks to reacquire this metal quantitatively can account, again, at least in part, from the bulk metal silicate fractionation. Okay, how about fractionation of volatile from common siderophiles? Well, here's an example of the gold to nickel ratio. We see it goes down from H2L to LL. In chondrules, according to Grossman and Wasson, gold oxidizes to a greater extent than nickel. The more reduced ordinary chondrite groups contain higher proportions of metal-bearing type 1 chondrules. When some of these chondrules lost metal globules during chondrule melting, more gold is retained in the silicate portion of the chondrule, and the chondrules thus developed higher gold to nickel ratios. These were inherited by the hole rock during agglomeration. So the conclusions. I know I'm rushing pretty fast, but there's a game on. 2A irons are the fourth major ordinary chondrite group. Their compositions lie along extensions of many LLLH trends. The order of formation was 2E, then H, then L, then LL. The 2E irons acquired higher proportions of the type 1 chondrules, the low FeO chondrules, and these chondrules had higher concentrations of refractory metal nugget-bearing CAIs. The 2E irons agglomerated early, incorporated sufficient aluminum-26 to undergo partial differentiation. A portion of the metal sulfide melt drained to the core of the asteroid to form a dynamo. The alkali-rich clasts in the 2Es were formed by preferential melting of plagioclase during collisional heating of residual silicate material in the crust and the mantle. The remaining silicate material in the crust and the mantle was metamorphosed to petrologic type 6, giving us these chondritic clasts that we see. The chemical fractionations involving metal among the chondrite groups were due, in part, at least, to the expulsion of metal-rich globules from chondrules during melting. We get the siderophile from lithophile, i.e. the metal silicate fractionation ratio, the refractory siderophile from common siderophiles, epitomized by iridium nickel, refractory siderophiles from volatiles, for example, iridium gallium, and the volatile from common siderophiles, showing the gold to nickel ratio over here. So that's all I have for you today. I know I rushed through it, but I'll be happy to answer any questions.
Okay, well, thank you, Alan. Yes, that was quite a fire hose of information.
It wasn't.
But there are a lot of enumerated points, and so there may be various questions that people have, and I'll just I don't see anything in the chat, so I'll just ask people to go ahead and unmute themselves. So you can raise your hand if you want, but otherwise just unmute yourself and say who you are, because it can be hard to figure out on the Zoom boxes, and go ahead and ask a question.
I have a question. I'm Bill Makuska, and it's listed under Dorothy Makuska. Anyway, my question is, what is the reducing agent?
Oh, well, that's a good question. People have suggested that. Could be hydrogen gas, it could be carbon. I'm guessing that in many cases in the ordinary chondrites, it's carbon that's around, because we see in some impact melted ordinary chondrites, like Portales Valley, we see big graphite inclusions. And we see some graphite-bearing clasts and some ordinary chondrite breccias. And of course, in enstatite chondrites, which are most reduced, we have a lot of native graphite there as well. I'm guessing that graphite or carbon is the most likely reducing agent, the most prominent one, more so than hydrogen.
Thank you.
Okay, thanks. Other questions, Paul?
Hi, Alan. Early in the talk, you were telling us about the two copper types, main type and copper-rich type 2Es. I didn't. If you came back to that, I didn't hear it. What does that have to do with all the other stuff you told us about?
Well, the copper-rich ones are also happen to be rich in troilite, and they tend to have, well, many of them have low cooling rates, but they're the ones that are most likely to be in the core of the body, because we would separate an FeS-rich melt from there. The copper-rich ones also are troilite-rich, and they may be the ones that formed in the asteroidal core primarily. And the copper-poor ones, the main set, are more likely to be the mantle rustites.
May I follow up?
Please.
So you showed the data for copper, and
Yes.
I'm thinking you must have, the classification copper rich and copper poor must include some other parameter, because there's overlap. Some of the main types had higher copper than some of the copper rich.
That's right. But this is from Watson 2017 paper. And there's a diagram which I showed. I went over it pretty quickly, I'm afraid. And even though the absolute abundance there, you can draw a sort of a diagonal line across it, and all the copper rich ones, or the main set, is separated from the other ones. You can do two of them. You can separate them cleanly on this copper whatever diagram it was. But the line isn't horizontal. It's at an angle. It's at a diagonal. These are Watson's definitions, and one can quibble with them. But I'm just following that. It's not my main point.
Okay.
Other questions? Well, I have a question and then a sort of philosophical comment / question. So the question is, in terms of the other isotopic compositions, the nucleosynthetic compositions, do the 2E irons relate to the ordinary chondrites on, these plots that Paul has made famous, for example?
Oh yeah, the 2Es are similar to H chondrites. They're non-carbonaceous.
Right. Okay. So that's what I would have expected. I don't have all the points on that plot committed.
And there's a couple ungroup irons like Gwyn, which is ungrouped, but again has alkali-rich class like 2Es that has an L-like oxygen isotopic composition, also a non-carbonation would fall on Warren 2011 diagrams.
So my sort of philosophical point here, let's see how I can put this. Other than I understand that you've clearly demonstrated a relationship between the ordinary chondrites and this group of iron meteorites, but philosophically, why would you want to call this a chondrite when it's coming from a parent body that you say has been melted and differentiated? And doesn't this muddle classification schemes unnecessarily?
Well, first, if we remove the word unnecessarily, yes, it does muddle classification schemes. So the real world is messy, as everyone knows. And I have to point out that these that 4 of these 2E irons contain chondrites, contain chondrite class with chondrules in them. They're not foreign objects that came in. They're chondrite class, and I'm just following this. Let me finish. Just following this logical progression. That how do we account for this? These things are clearly related to ordinary chondrites, and they have chondrite class. These chondrite class again fall along all these trends. So I think the easiest way to account for that is to say it accreted earlier, which makes sense because they're more reduced. They have higher proportions of type 1 chondrules. And the refractory metal nuggets in them would have accreted early. I think all this logically holds together, and the fact that it muddies the waters, that an iron meteorite group is now a chondrite group, it's just too bad.
Yeah, I have to register that I don't like it, because I think the most clear definition in terms of trying to put a hierarchy or classification on meteorites are those that were, melted and chemically and physically differentiated, and those that didn't undergo this planetary process. Because you could take the point of view that, you gather anything together depending on how you want to define chondritic abundances, gather any sufficiently reasonable amount of material together in the solar nebula, you can just say it's chondritic, right? I mean, the Earth is the biggest chondrite, right, in the inner solar system. That's how we model it anyway.
Even the metal fraction of these, in addition to the 2Es having these chondritic class with chondrules, even the metal fractions, again, fall along all these ordinary chondrite trends in their siderophile abundances, which that has to be explained rather than saying, well, they're chondrites, they don't belong. Also, to make things also muddy, we have the lodronites and the Acapulcoites, some of the Acapulcoites have chondrules in them, and some of the Winonaites have chondrules in them as well. So the main models for those things are partially differentiated bodies. That may be correct. I've been partial to impacts of it, but I think after my 2E study, I may throw in the towel of impacts and suggest that partial differentiation may also be viable for them. But again, so we see that partial differentiation is a real process apparently, and has formed, you know, the Acapulcoites, the Winonaites, the 2E irons,
Right.
material.
All right. Well, I don't want to belabor it. I think I've made my point there, and I know that Steve Desch agrees with me, saying that, you know, we call things like lodronites, winonanites, you know, primitive achondrites. So they're
That's true. That's Marty Prince called them that. Steve Desch also doesn't have the H, L, and L forming in order. He has a funny order for them. L's forming for H's and then L's later or something like that. And I've argued with him about that, and I can't believe it.
Hi.
we might as well give Steve a chance. And then Don Brownlee has a comment, or a question, but I'm going to have to give Steve a chance to respond to that.
Sure.
Thanks.
Real time.
Yeah, no, I do find it compelling that these 2Es are associated with ordinary chondrites. They've probably formed first. I think that's all compelling. The difference, and you don't give a difference in time between the formations of HLs and LLs. You're just saying there's an order in which they were oxidized sequentially, but there's no time.
Not enough data. Yeah.
Well, in our 2018 model, yeah, we do predict they all form pretty much at the same time. H like a little bit later, 2.1 instead of 2.0. But to me, it's not so much a time in the nebula. It's just that H is formed over a wider range of radii, and therefore, you know, some of them could have formed later, you know, but overall, they probably formed from less oxidized material, as you say. I'm saying the differences are slight, not worth arguing about.
Okay, so on that degree of harmony, let me go to a question that Don Brownlee put into the chat. How common are 2E inclusions in unequilibrated ordinary chondrites?
Oh, the answer is very simple, 0.
Okay.
But let me just say that it's very uncommon to find an intact ordinary chondrite of one type inside another. I think there are only 2 examples. There's the H chondrite class in St. Mesmin, which is an LL, which Bob Dodd found, and then there's an LL5 class in the Dibit H chondrite regular spectra, which I found. And other than that, I think there are no examples of one ordinary chondrite type inside another that have been reported. There's some that have oxygen isotopes that are impact melt class that are similar to something else, but no intact ones. So it isn't surprising that we don't find 2Es. Besides, if we had a little class in some H chondrite with chondrules that are just on average slightly smaller, you might find it hard to see. If we have a little bit of a metal nodule in an H chondrite, it might be difficult to discern to begin with. So they might be there, but anyway, the bottom line is it's very rare to have any identifiable class of one ordinary chondrite type inside another at all.
Don, is that okay, or do you want to follow up?
That's fine.
Okay.
A little laconic, I think. But
Okay. Other questions?
Alan, this is Peng. Thanks for the nice talk. I have a question kind of related to what Paul Warren was asking. You showed earlier that there are 2 groups of 2Es with high and low copper. That just reminded me that copper along with chromium has been historically difficult to model with the experimental partitioning data. Do you think the correlation of troilite and the high copper in 2Es, does that give any kind of clue to the difficulty of modeling the copper data in iron meteorites in general?
It may well be. I mean, there's this big correlation there that John Wasson found and put it in his 2017 paper. I'm just reporting it. I understand that copper is difficult to model. Wasson had actually tried to plot things against copper for a while, and then he sort of gave that up. And it may be. I haven't looked into it much, and I'm just reporting the extant fact that Wasson reported in his 2017 paper of these two groups. And Ed Scott believed it too, because in his 2020 paper for Oxford Research Encyclopedia, Ed also talked about the copper-rich and copper-poor 2Es.
Okay, thank you.
Okay, thank you. Any other questions, comments,
Innuendo.
dedications, requests? Well, I think we've had a good discussion, and we've certainly, I've certainly learned a lot. So thank you, Alan. Thanks very much.
Thank you all for
And,
coming and enduring the hardships of trying to navigate your way to the talk.
yes, yes. So thanks. Anybody, obviously, you all figured out how to get here. Was it appreciably more difficult than other months? No? Okay.
Yes. Yes.
Yes, okay, yeah, I just can explain what happens is there's this list, and when we send a notice out to the list, it goes to another program on another computer, which I found out today, strips out all the links. And so when I would cleverly put in things like click here to open the Zoom, those links were all taken out, as was all the formatting and everything. So we'll try to figure out how to do that, or we'll find another way to communicate with the list. So sorry about any confusion on that. This is the post-Juliet era that we're bumbling through. But just I guess the one announcement is that you know, our next lecture in this series will be again the third Sunday of the month in February. And do we have a title, right? Alan, do you remember?
I don't have a title offhand. Lawrence Garvey is giving.
Lawrence Garvey is our speaker, and so you'll get an announcement about that.
Right.
Okay, well, thanks everybody for joining us today, and
You can stop
now I see James has got his Chiefs shirt on. I'm going to throw on my Giants jersey and hope for the best. You know, it's the first time in 6 years we get to do this. So for some long-suffering fans, so Paul and I will be rooting for the right team. No offense to any of you good Vikings out there, but I hope you lose today.
Go G-Men.
That's right. All right, take care, everybody.
Bye. Thank you,
Thank
Kevin.
you, bye.
Bye.
Stop the recording, right?